What does standardization mean? What does that mean? If I standardize the solution, what does that mean? He said to utter silence.
Like figuring out the molarity?
Yeah, basically calculating the precise molarity. And the reason we need to do that is that when we make, especially when we make a solution of acids or bases, it's critical to do that because when you make a solution in the lab, I sort of go into it a little bit in the discussion. We use something called, let me get my pen ready. We use something called deionized water. Two reasons. One is the fact that we use deionized water. And when we use deionized water, basically what it does is it takes all of the metal ions out. So it subtracts the metal ions from the water, but it replaces them with H plus or H3O ions. And these are the same things. You'll see these used interchangeably. H plus, this is called the hydrogen ion, of course, and this is called a hydronium ion. And it's because H plus generally reacts with water and forms this. So either one. So if the metal ions are removed and more H plus is added, that means the pH of this solution goes down, sometimes dramatically down. So if we're trying to get a precise pH of something, it's really important to balance out the acids and the bases. The other reason why it's important to do a standardization is when we breathe out, we know we breathe out water and CO2, right? Anyone know what happens when you mix CO2 and water together? You know what you get?
Do you get a carbonate?
Yeah, you do. You actually do. You get H2CO3, which is carbonic acid. Yeah, it's hydrogen carbonate. Very good. Yeah, you get carbonic acid. So if I breathe, so if you have just pure water, let's say you have pure water and it has perfectly balanced pH. It has exactly the same number of H plus and OH minus in it. It's pH 7.000. It is like pristine, pure water. The minute you open it, there's CO2 in the atmosphere, as we know, and the CO2 is going to dissolve in the water and form carbonic acid. In fact, it's you breathing, it's you taking in CO2 in your lungs and mixing with acid that allows the pH balance of your blood to remain stable, because the amount of carbonic acid in your blood basically keeps the pH about where it should be. So it's an important reaction, but it's a pain in the tuchus for those of us who want to have perfect pH or perfect concentrations of H plus or OH minus in a solution. So when we take some sodium hydroxide, we take some solid sodium hydroxide, we measure out precise mass, we figure out how many moles that would be, and we put it in the water, and we dissolve it, and mix it up, and we say, okay, now I have a perfect 1.000 molar solution of sodium hydroxide. No, you don't, because some CO2 has been dissolved in that water. It's formed carbonic acid, and it's reacted with some of your sodium hydroxide. And so your concentration of sodium hydroxide, what do you think now would go up or go down? if you have a little more acid in your water than you expect, and then you mix sodium hydroxide in it, is it going to increase your concentration of sodium hydroxide in solution? Is it going to decrease the solution of hydroxide ions in solution? What do you think? Here's the reaction. H plus plus OH minus makes water, right? That's the basic reaction we're going to be doing today. That is a neutralization reaction. In other words, you take acid and you take base, and they neutralize each other and form water. So if I have more acid in my solution, what do you think that's going to do to the concentration of my base?
An increase?
It's going to what?
An increase? Maybe?
Why would it increase it? Can you explain? You figure they would both increase together and form water?
Would it be the pH will be lower? Because
I
you're
think it would
increasing
be
the
the
acid.
same.
Well, the pH is lower than I expect because there's more H plus than I expected because of the presence of CO2. So yeah, there's going to be more H plus than I want. So because there's more H plus in the water, is that going to decrease my hydroxide ion concentration or increase my hydroxide ion concentration?
It may be same.
I'm sorry, it will what?
It may be the same.
It'll be the
since we just,
same.
like, yeah, since we just break the bond between them.
And we're not breaking a bond, we're actually forming one, right? We're taking H plus here, and we're taking OH minus, and we're forming a bond. So we're actually making bonds.
So I remember you said whatever in reactant should be the same in the product concentration. That's why I think it will be the same.
Would it be you'll just have more acid left over?
No, think of it here. Let me get a whiteboard. Okay. So here's the situation. So I have a solution, and I have put hydroxide ions. I've dissolved sodium hydroxide in this solution. So I have hydroxide ions in this solution. As it turns out, I also have a lot more H plus in here than I thought. So there's more H plus than I thought there would be. And the reaction is H plus plus OH minus reacts to form water. So if there's H plus, if there's more H plus ions than I expected, will I have a higher than expected amount of sodium, of hydroxide ions, or a lower amount? So look at the reaction. For every H plus that's there, it consumes a hydroxide ion and makes water. So the presence of H plus does what to the concentration of hydroxide ions? In other words, if there's no H plus there, this reaction doesn't happen, and my hydroxide ions remain the same concentration. But because there is H plus ions present, this reaction does go forward, and I do make additional water. So what's going to happen to the amount of hydroxide ions? Is it going to go up, or is it going to go down? So without any H plus, it stays the same. But in the presence of H plus, some amount of OH minus gets converted to water. So if H plus is around, do I have less hydroxide ions or more? Or the same?
either same or decrease.
It's one or the other.
You would have less.
Why? So the more H plus I add, what happens to my OH minus concentration?
Decrease.
How come?
Because when you add OH, the H plus will react with OH, which means we consume H.
That's right. Well, no, well, yes, the other way around, but yeah, the more H plus is present in my solution, the more hydroxide ion it consumes and the more water I make.
Okay.
So if I make a 1.000 molar solution of sodium hydroxide, that's an ionic. So that turns to 1 molar solution of sodium and a 1 molar solution of hydroxide ion that completely ionizes. So I use this solution assuming that I have perfect 1.000 molar sodium hydroxide. However, if I use deionized water, or if there's in the presence of CO2, which also makes acid, I'm going to have less than that. I'm going to have like, 0.996 or 0.992 or some smaller concentration. I don't know what smaller concentration it is. But if I'm going to use this to titrate something later, and that's what we're going to do in the second part of the experiment, I'm going to use that solution to exactly measure the amount of acid in a solution. I can't do that precisely if I don't know what the actual concentration is. And so the first part of the experiment is to determine precisely what my amount of sodium hydroxide is by basically titrating it. Can someone tell me what titrate means? What's the meaning of that word, titration?
Exact volume of one substance is reacted with a precise amount of another substance.
Yeah, more or less. But it's particular for this. It's particular for an acid-base reaction. It's when I want to measure, basically when I want to measure either the concentration of H plus or the concentration of OH minus. And I do that by having one of these in a very precise concentration and then adding it to the other one until they balance perfectly. And when they balance perfectly, then my pH basically goes to 7 when they're precisely the same. And so we're not always going to have a pH meter to measure it, but when we get really, really close to them balancing out, the pH changes rapidly. Because if you remember, pH is a measure of 10 to the minus whatever this number is. Oops. 10 to the minus 7 is pH 7, right? So basically we're measuring really small changes in concentration. And so our pH is going to change radically from there being like more acid than base to being more base than acid. And so the pH is going to go wildly different. And that's when we're going to use something called an indicator. So what's the indicator do? You remember, what's the indicator in this experiment? You remember what it is, what it's called?
Phenolphthalein?
Phenolphthalein, right, it's phenolphthalein. What does it do?
It just tells what the pH level is.
How? How do we know what the...
It tells the end point of the reaction, like when is the reaction already happened.
Yeah, but how do we know? What does it mean? Does it do something? Does it light up? Does it catch on fire? I mean,
Well, it'll be
how does it tell us?
colorless. It'll be colorless in acidic solution and then pink in basic solution.
That's right. That's right. So we use it when we start with something acidic, because basically at a pH below 7, it's colorless. You don't really see it. But then if you add base to it, The minute it goes a little bit, minute it gets like pH, I think around 7.5 or 8, then it changes pink. And if it goes way beyond pH 8, it gets really dark pink. You can see it in the lab. If we were doing it in the lab, it's really quite dramatic. It goes from because what you want is a very pale pink. And if you add too much, it's just pink. It's just really, really dark, and that's too much. So basically, when you're doing a titration, you want to be as close to that point where the base exceeds the acid concentration as possible. You want to be like half a drop of liquid past, because it's basically impossible to get it exactly the same. Because the minute you go even a tiny amount, like, a 100th of a milliliter over the equivalent, and we call that the equivalence point, when you have the equal concentration of acid and base. Once you even go a tiny bit beyond it, the pH goes way up. And so you can either follow a titration with a pH meter, or you can use an indicator like phenolphthalein that changes color. All right, so let's go back to the online lab. Here we go. So first we're going to do a standardization of the sodium hydroxide. We're going to get a solution of sodium hydroxide. It says it's 1.00 molar, but we don't know exactly what it is because it's got H plus in there from deionized water. It's got carbonic acid in there from people breathing in it, whatever. So it's going to be close to that, but it's not going to be exactly that. And so we'll do a standardization through a titration by adding an exact amount of a weak acid, like a very precise amount of weak acid. And then we'll titrate that solution of weak acid. And then once it gets to the equivalence point, we'll have precisely, what we'll do is we'll have precisely the right amount. We'll measure the amount of weak acid we add. We're going to use a weak acid called KHP. I'll explain what that is. We'll dissolve it in water, so we'll have an acidic solution, and then we'll add hydroxide ion in the form of sodium hydroxide to it until the moles of NaOH equal the moles of KHP. At that point, we will achieve the equivalence point, and the color will change. And so because we know exactly how much the mass of KHP and the molar mass of KHP, we can figure out how many moles of this we have. And we can figure out pretty precisely how many moles of NaOH we're going to need. We're going to need the same amount. So we're just going to add a solution of NaOH until these two things equal each other. And then we'll know exactly what our concentration is. So we're going to do that experiment first. And then the second experiment is we're going to take, instead of KHP, we're going to use an unknown acid. And we don't know what it is. All we're going to be able to do is measure the mass. So we're going to measure the mass of this unknown weak acid. And can anyone tell me what a weak acid is? What's the difference between a weak acid and a strong acid? What's a weak acid?
Is it closer to the base?
Sorry?
Is the weak acid closer to the base?
What do you mean by closer to the base? I don't know what that means.
It's not that strong of an acid.
Yeah, but I don't know. What does that mean? What's the difference in a weak acid and a strong acid?
So a strong acid would be like closer to 1, whereas a weak acid would be closer to a 7.
What's 1 and what's
For
7?
pH level. Sorry.
Okay, yeah, but why? Why? That's right, but I mean, why is that? What's the difference between them?
The number of H plus ion.
The number of H plus ions that from what? Where does the H plus ions come from?
From hydrogen.
Mm-hmm.
In the solution?
Mm-hmm. Yeah, so basically it's when you put them in a water solution. That's the key. So a strong acid, like HCl, I put that in water and I get H plus and Cl minus. It completely dissociates. So if I have a 1 molar solution of HCl, I also have a 1 molar solution of H plus and a 1 molar solution of Cl minus. Now, a weak acid like acetic acid, which is acetic acid, quick, H2, that, HCOOH. So this is a weak acid. So when it dissociates, so if I have a 1 molar solution of that, I only get a small concentration of H plus and a little bit of the anion formed. We call this the conjugate base. This is what's left over when the weak acid dissociates. So this, like for acetic acid, I only get about 5% of it dissociate, or actually less than that, around 1% dissociating. So instead of having like a 1 molar solution, I would have like a 0.01 molar solution of H plus. So someone else previously mentioned, yeah, so my pH would nearly be as low. If I dissolve a weak acid in solution, the pH doesn't change nearly as much as if I put a strong acid in solution. But what happens with a weak acid, so let me go down a little bit in the description. It's what we call a weak acid is defined by something we call an equilibrium constant. We're not going to get too much into equilibria, but what I sort of want you to see here is that sort of the acid is generally referred to as this. So it's H, which will become the H plus, and the A, and this could be anything. This could be, you know, acetate. It could be whatever is left over when the H dissociates and becomes H plus. So when that dissolves in water, I get H plus, or in this instance, H3O plus. And remember, that's the same thing. And H minus, this is what's left over. And this does not go to completion. HCl goes, H plus to Cl, goes to completion. All of this gets converted to H plus and Cl minus. So my concentration of HCl is exactly the same as the concentration of my H plus and my Cl minus. In this instance, my concentration of weak acid is far more than my concentration of H plus and A minus. And so we refer to calculate these things, we refer to something called an equilibrium constant. And we just figure out what's the concentration of my acid. And if Ka is very low, I'll have very little H plus. And if Ka, my dissociation is very high, I have a high concentration of H plus. But what I want you to remember is that if in the presence of a strong base, let me clear that. In the presence of a strong base, the strong base pushes that to completion. So if I have, so here I got my weak acid, got my same weak acid, HA, but instead of just dissolving it in water this time, now I throw some hydroxide ion in, which is a very strong base. Now what that is going to do is the hydroxide ion is going to forcibly remove the hydrogen from the weak base. It's going to basically just pull it off because its affinity for H plus is much, much higher than the weak acid. So it's just going to pull it off. And this reaction, as you can see with the air, when the arrow goes in one direction, it means that reaction goes to completion. When we have the arrow, when you have the arrow going in both directions, that means sometimes the reaction goes forward and sometimes the reaction goes backwards. Here, it just goes forward, so it goes to completion. So whatever the concentration of OH is will equal the concentration of the weak acid. So once that reaction goes to completion, if I can measure the concentration of this, I know what the concentration of this is. Okay, any questions about that? Now it's a little more of an advanced concept, but basically a strong acid will pull apart a weak base. If I put a weak acid, or a strong base will pull apart a weak acid. If I put a weak acid just in water by itself, very little of it will get pulled apart to H+. But in the presence of a strong base like hydroxide ion, it just pulls that hydrogen off. And it converts all of it to water and A-. Any questions about that? I know it's a lot to take in. But basically what it means is we can figure out the moles of a weak acid by measuring the moles of a strong base, because they'll equal each other. Yeah, so gotta be some questions about this. Any questions? Yeah.
Basically, you said if it's strong acid, it's gonna be like the reaction will be happen, but if weak acid, it will not be able, like there is no change.
No, there's a change. So with a strong acid, so let's say I've got hydrobromic acid. I dissolve hydrobromic acid in water. All of it goes to H+ and Br-. All of it gets converted. I put a weak acid, like H, and we're just using A. A could be anything like acetate or lactate or whatever the acid is. When I put that in water, only a small amount of it goes to H+ and A-. Very, very little, like maybe less than 1%. And so the pH doesn't change nearly as much, which is good. I mean, if you're eating a lemon that has citric acid in it, you don't want citric acid to be super, super strong, or it'll just burn your mouth off. You sort of like the taste is nice for like a little bit of acidity, but you don't want a whole bunch of it because it'll burn. So weak acids like citric acid, add a good taste to something because they're weak, because they don't give that really, really, really strong acid taste, just a little bit. Any other questions? Oh, as we go through this, hopefully it'll start to make a little more sense. So is everyone just completely confused because we haven't had a chance to read this yet? Hopefully it'll make more sense when you read it. Let's do the first question together, and then we'll start. Because this is the first reaction. This is the first reaction basically we're going to do. So KHP is a weak acid, and when it dissolves in water in the presence of a strong base, so here's our strong base, sodium hydroxide. So that gives us, we know it's a strong base because we dissolve it in water. All of it gets converted to sodium plus and hydroxide minus. So my reaction is the hydroxide ions react with the KHP and they pull this hydrogen off right there. Just pull it off because it's being held onto very sort of loosely by weak acid. That's basically what a weak acid is. It means it's holding on to a hydrogen with a very weak bond that's easy to break. And classically, the bond is this. This is what most organic acids look like. So here's oxygen, and it's holding on to this hydrogen. But this particular bond is very weak, and so it breaks easily. And so if you have something like hydroxide come by, can actually pull that off. and leave you with this. Now the oxygen has a negative charge on it and water is produced. So that's the reaction that's taking place. Strong base pulls that hydrogen off, leaves you with a negatively charged anion and water. And this is the reaction here. So it leaves you, so the hydroxide pulls this hydrogen off, makes water, and leaves you with this. And notice it's got a negative charge on it, and the hydrogen is gone. Okay? So the question is, if we know exactly how much of this weak acid we have, can we figure out how much sodium hydroxide it takes to titrate it? And remember, when we say titrate, what we're actually saying is basically adding enough sodium hydroxide so that the moles of hydroxide exactly equal the moles of weak acid. And so in order to do that, we need to look at the reaction. What's the molar ratio of hydroxide to KHP in this reaction? This reaction right here. This is our KHP. And there's our hydroxide. What's the molar ratio of KHP to hydroxide?
1 to 1.
Mm-hmm. Exactly. So that means one mole of KHP will react with exactly 1 mole of hydroxide ions, and this reaction goes to completion because the arrow is just pointing in one direction to make water and leave you with a KHP anion. So if I know precisely how many moles of KHP I have, I can calculate exactly how many moles of hydroxide ion I need. So if I have 1 mole of KHP, how many moles of hydroxide ion do I need?
1.
1, exactly. It's a 1-to-1 ratio. That's not always going to be the case because some acids have more than 1 hydrogen. For instance, phosphoric acid has 3. So I would need 3 moles of hydroxide ion to convert that to phosphate in 3 moles of water. So that's why I always need to do the reaction and balance it, make sure it's balanced. Because in this instance, if I had 1 mole of phosphoric acid, I would need 3 moles of hydroxide ion to titrate it. This is what we call a triprotic acid. Tri for 3 and protic for proton or H+. So a monoprotic acid loses 1 proton. A diprotic acid loses how many?
2,
So 2. And a triprotic acid loses,
3,
and a tetraprotic acid loses
4.
4. There's not too many of those, but there's a couple. But in this instance, we see it's a 1-to-1 ratio. That tells us it's monoprotic. So let's do the calculation. So I have 0.128 gram sample of KHP. So I write down what I know, 0.128 grams of KHP. What do I need to convert that to?
2 mole of KHP.
Damn skippy I do. How am I going to do that?
1 mole of KHP over 204.23 grams
Oh,
of KHP.
man. You guys are getting this big time. Converting moles from grams like a boss. Okay, so how many moles is that, KHP? I'm working on it too. 1.28.
6.267 moles of KHP.
1.23. Yep, so at 0.000627 moles. And remember, I can use as many digits as I want here. Don't round too early. I could use 18 significant digits if I want. I don't have 18 significant digits, but I can use as many digits as I want until I get to the end. So that's how many moles of KHP I have. So we know when I reach the end point, when the phenolphthalein changes color, that means that the number of moles of hydroxide and the number of moles of KHP are now the same. So at the end point, how many moles of hydroxide do I have?
You have 1 mole over 1.
I have a 1-to-1 ratio, yes,
Ratio.
but how many actual moles of sodium hydroxide or hydroxide ion? How many moles of hydroxide ion do I have?
The same as KHP.
The same as KHP, right? That equals the number of moles of KHP and equals the number of moles of hydroxide ion, which also equals the number of moles of sodium hydroxide. Why? Because when I dissolve sodium hydroxide in water, it's a strong base and all of it dissociates into sodium and hydroxide. So whatever my concentration of sodium hydroxide, that's also the concentration of my hydroxide ion because it's a strong base. And a strong base, just like a strong acid, dissociates completely, becomes ionized. So now I know what my moles of sodium hydroxide is, and I know how the volume of sodium hydroxide that has that many moles in it. How am I going to calculate the concentration of my sodium hydroxide?
You have to convert the volume to liters first.
Okay, how many liters is that?
28.54 milliliters over 1,000.
0.028.
28.54 divided by 1,000, or multiplied by 1 over 1,000. Sorry, always multiply. So that's 0.02854 liters, right? So I've got moles and I got liters. How am I going to get my concentration?
Moles divided by liters.
Damn Skippy again. Yes, moles divided by liters. That's what molarity is. That's what capital M means. It means moles over liters. So here's my moles, and here's my liters, 0.02854 liters. So now I have moles over liters, and so my concentration is 0.0006267 divided by 0.02854. What do you guys get?
Point 0.02197.
Yeah, 0.00219. I got 6, but or 5.8.
96, sorry.
Yeah, whatever. All right, molar. So that's an answer. And remember, we put the units in, molar. How many significant digits should be in my final answer?
3.
That's right. I have 5 significant digits in the molar mass. I have 4 significant digits in the volume, but I only have 3 in the mass of KHP. So I'm limited. I'm limited to 3 significant digits. So what am I going to do with that number?
So M equals 0.0220.
Yes, very good. Yeah, 0.0220. And the 0 is required because this tells us we have 3 significant digits. We could also convert that to 22.0 millimolar. We could also call it that. So yeah, 0.0220, 3 significant digits. Okay. So any questions about how to do the conversions of when you at equivalence point, when the pH changes radically, when you have the same amount of moles of acid and base, that's the equivalence point. That's when the moles equal the same. And that's how we can calculate moles of acid and moles of base. One of them's known, one of them's unknown, but at the equivalence point, they're equal. That's how we use titration to figure out concentrations. Any questions about how to do that?
The final answer is 0.021958. This is the final answer.
No, final answer is 0.0220 molar, because we need 3 significant digits. Because the smallest number of significant digits in all of these calculations is the mass. And there's only 3 significant digits, 0.128. So 1, 2, 8 are 3 significant digits. All right, let's look at the instructions for the lab. So we're gonna.
So quick question.
Yeah.
Was the questions 1, 2, are they supposed to be the pre-lab questions?
Yeah, you can include them in your lab report. Yeah, you don't have to do them.
Okay.
You don't have to submit them separately.
Oh, okay. But they're considered pre-lab questions, right? Okay.
Yeah. And the second one's basically, exactly the same. All right. So, as I mentioned, when you make a concentration of an acid or a base, really, you're not going to know precisely what it is because of the presence of carbonic acid, the presence of extra H+. So what you do in that situation is that you add a known amount of acid, in this instance, KHP. And we use that because basically it doesn't react with anything until you put it in water, and you can measure the mass very precisely. So we're going to dissolve that in some water. We'll put it we'll weigh some out, put it in a beaker, and then we're going to fill a burette. Anyone tell me what a burette is? What's a burette? I think we haven't mentioned burette before. You know what one is?
I know it's like a long tube.
Yes, you've probably done a titration in high school, I imagine. It's a fairly standard experiment to do. Yeah, it's a very long tube, very long, and it has a stopcock on the bottom that you can turn and lets, just small drops of water come out, or solution, whatever it is. And you can measure the volume of liquid that you've added very precisely. So it's got gradations on the side, and we'll see what one looks like in the virtual lab. It has gradations on the side of it. So this was my burette. It would have gradations up and down that I could read. I'd look at it and see the level of solution going down. And I should be able to measure that volume to like 4 significant figures. So you get very precise measurements of volume, okay? So we put our weak acid solid. It's a solid when it's dry, and we dissolve it in water. We fill up this with our 1 molar sodium hydroxide, and then we just turn the stopcock and allow the liquid to flow down into the KHP water solution. After we've added a little bit of indicator, because we need to know when the pH changes. So in the beginning of this reaction, should my solution be clear or should it be pink? When I haven't added any sodium hydroxide, I just have my KHP and water. Should that be clear solution or pink with the phenolphthalein in it?
Pink.
When does the phenolphthalein change color? When it's acidic or when it's basic? When it's low
When
pH?
it's it changes color when it's low at pH. No, high pH.
High pH. And what does high pH mean? That means more acid or more base?
More base, so it's colorless.
More base, right. So it's acidic at the beginning because even though I have a weak acid in there, it's still an acid. So the pH is going to be less than 7. It'll be, and actually we'll be able to see because when we put it in the beaker, we can click on it and see what the pH is. You can actually follow the pH as you do the titration. So yeah, the pH will be low. It'll be like, between 3 and 4, I think, something around there. And so notice as you add sodium hydroxide, the pH isn't going to change very much at first. And you're going to add more and more. And the reason why it isn't going to change much at first is that the hydroxide is going to be consumed by the KHP and converted to water. And we know that just water doesn't change the pH very much. It's just water. And so we're going to add more and more and more and more hydroxide. And the pH really isn't going to change very much. It'll change very little. But then when we get very close to all of the KHP being consumed and converting the hydroxide to water, once we get really close, the pH will change dramatically. And the pH will go from being low to being really close to 7 and then going past it. And at that point, the phenolphthalein changes color and becomes pink. At that point, we have precisely the same amount of KHP and hydroxide. But what you need to avoid is adding way too much sodium hydroxide because that color is pink too. I mean, that's also pink. So basically what you want to do is figure out how much sodium hydroxide you're going to need, add about 85 to 90% of that volume, and then drop by drop add it until it just turns pink and then stop. And then I'll show you how you can do that. Okay, so then once we get our volume of sodium hydroxide, we figure out our moles of KHP, which we should have figured out at the beginning already. That'll give us moles of NaOH, which will be the same because it's a 1-to-1 ratio. We have our moles of sodium hydroxide, we'll have a volume of sodium hydroxide, and that'll give us a concentration of sodium hydroxide in molar, okay? So why don't we try that, and then we'll come back and talk about the second experiment, which is pretty much the same thing, except first experiment, we know what the acid is, and we calculate the hydroxide. Second one, now we know the hydroxide, and we calculate an acid. So it's basically the same experiment, but reversed, okay? So let's go to the first website. So hopefully it's not going to be a problem.
For part 1, do we do the same titration like 3 times?
Yes.
So like 3 trials?
Mm-hmm.
Okay.
Yeah, and you should get hopefully you get the same amount every time. Okay, so here is so I'm at 128 here. Here's my workbench. Can everyone see the workbench okay? Everyone got one in front of them as well? Does everyone have one in front of them, hopefully?
Yes.
Yes.
All right, cool. So let's go to glassware, and we'll get our beaker. So we'll put that in here. That's where we're going to add our acid and our water. So notice when I click on the beaker, I get information about it. Its volume, none. and it's 25 degrees. That's another thing I want you to pay attention to. It'll give you the temperature of the reaction and see if you notice anything about it, because it relates to something we'll be doing later quite nicely. So solutions. I want some water. So I'll put, like, let's say 50 mils of water in here. The amount of water we put in there doesn't really matter. Can someone tell me why that is? We could add 20 mils of water, we could add 50 mils of water, we could add 100 mils of water, and it doesn't really matter. How come?
Because water is neutralized. I think.
No, not really. It's not going to affect the titration. How come my volume of water won't really affect the titration? What am I actually titrating?
Is it because water is basically neutral pH level? So it's not going to affect the.
That's one reason. What's the real reason I'm looking for? I mean, is the water involved in the reaction?
No.
No. What are we actually titrating? We're titrating one thing and another thing. What are the two things we're actually titrating?
The acid.
The acid
The base.
and the base. We're titrating the moles of acid and moles of base. It doesn't matter what the volume is. It doesn't change the number of moles. So I could do this reaction in 10 mils, or I could do it in 100 mils. It doesn't change the moles of acid and base. It doesn't do that. Pretty much the only reason for doing it in a small volume, so when you add your indicator, you can see it better. That's pretty much it. If I have one drop of phenolphthalein in 100 mils, it's kind of harder to see the color change than if I have one drop of phenolphthalein in, like, say, 10 mils. That's the only reason. So let's just put, I don't know, we'll put 50 mils in there. It doesn't really matter. We just need some water to dissolve our acid in. So we drag it over. I'm going to put 50. Let's put 50. Okay. And click off of it. Then I can get rid of this. I don't really need it anymore. Remove. Then I'm going to go down to KHP. Now, it's potassium hydrogen phthalate. That's what the KHP actually stands for. Potassium hydrogen phthalate. And so when it dissolves in acid, or when it dissolves in the water, it loses some of that hydrogen as H+. And then when we add the hydroxide ion, it pulls all the hydrogen off of it, and you're just left with potassium phthalate. Okay? So KHP. So I'm going to drag the KHP over, and I'm going to add, and now I want to be precise. Okay? So now I'm going to put 1.00 grams and pour it in there. Notice what happened to the pH. Now, what happened to the pH of my solution?
It decreased.
Yeah, it went down. How come? Why did it do that? What did I dissolve in it? I put my KHP in there. And what is KHP?
Because it's acid, so it will decrease the pH since acid is basically low pH.
Yeah, an acid means, what an acid actually is something that when you dissolve it in water, releases protons, releases H+, makes hydronium ion, all the same thing. It releases H+ into the water. So even a weak acid's going to do that, or else it wouldn't be an acid, right? So when we dissolve it in water, it's going to release some H+ into the water. And when it does that, the concentration of H+ goes up, and the pH goes down. So now we know we've dissolved a weak acid. in there. It's got 3.28. So it means the pH has gone down. It means we have more H plus. It means must be a weak acid in there. So go back to my stock room, get the phenolphthalein indicator, drag that out there. And I'm gonna put like a milliliter in there. It doesn't really matter. Because we just want it to change color. And then I'm not gonna need this. I can remove that.
How much you add?
Like a mill.
Okay.
Doesn't really matter. You can put 2 mils, you can put 10 mils in if you want. Now I want to get my burette. So click on glassware, go to other, and I go down 50 mil burette. That's what I want. Hey, Raj. Can you say hi to the class?
Hi.
He's a budding chemist. Hopefully it'll be something more interesting, but you never know. All right, so my burette, but right now it's empty. So notice it has 0.000 mils on it, so it doesn't have anything in it. So we need to add something to it. So I come back to solutions, and I come down to, see it says approximately 1 molar sodium hydroxide. So someone made this solution. It's around 1 molar, but we don't know exactly how much. Maybe they didn't weigh it very precisely. So they just just threw some sodium hydroxide in there, but we don't really know what the concentration is. It's around 1 molar. So we're gonna take that out, drag it over the burette, and we're gonna fill the burette up. Now, when we do that, notice, let me get my, notice we get this drawing, basically. This is what the top of the burette is going to look like. And when you pour in the sodium hydroxide, it may not go exactly to 50. We'll see that here. I'm going to say add 50 mils. Add 50. Pour. And look what happened. It didn't fill it all the way to the top, because there's a little bit of dead space at the bottom of the burette. So if you want to fill it all the way to the top, you'll need to add some more, or just make a note of what the volume is right now. What would you say the volume in the burette is right now?
I'm sorry, just I want to ask you, how you get the burette, from which icon?
Oh, go to the stock room, go to glassware, other glassware, and then scroll down to burette. It's right there.
Okay.
Okay? So what is my volume of solution in my burette right now?
49 ml.
Nope. No, just read it right off.
Oh.
2. 2 what though? 2 is not a good number. 2, because we can measure it more precisely than 2, right? I mean, this is a burette. We want very precise volumes. So you want to read. Let me just erase that. You want to be able to read, and you can zoom in if you want. Why don't I do that? We can zoom in here. That's better. Yeah, we can zoom in and try and read what that volume is. So basically what I want, so each one of those large marks is a mil, 1 ml. And each one of these small marks is 0.1 ml. So what is that? What would you call that as a volume?
2 milliliters?
Nope.
Or is it 20? It's kind of hard.
It is 2, but you're not saying it correctly.
2 milliliters.
I would not say that that is 2.
2.0 milliliters?
I'd
Or
say it's
2.1?
more accurate than that.
2.1 ml.
No, 2.1 would be right there. That's 2.1.
2.00 milliliters.
There you go. Yeah, it is right on. We can tell the difference between 2.1 and 2.0, right? So if it was halfway in between, we could say that that was 2.05. We can say that because we can, because what you do, remember, when you're measuring anything, you get as many significant digits as you can from the instrument you're using, and you always estimate the last significant digit. So we can clearly see that it's 2. All right, 2. We can clearly see that it's not 1.9 and it's not 2.1, right? Would you say it's neither of those things? Would you say it's clearly not 1.9 or 2.1?
Yes.
You would say that, right? So this second one is also given to us by the instrument. But the third digit, we have to estimate. So, I mean, if we looked really, really closely, we might see that it's just a tiny bit above 2.0. So someone might look at that in the lab and say, that's 2.01, and somebody else might say it's 2.02. And both of those would be fine. Both of those are legitimate measurements because this is given, and you estimate that one. But all three are significant. All three of those numbers are significant. So what we're going to do is write down our volume, our initial volume, before we did anything. So our volume initial is 2.00 mils. So we would write that in our notebooks. Initial volume, 2.00 ml, okay? Now I'm going to clear all this out. So I'm going to write that down my own self because we're going to do the calculations together for the first one.
So I have a question.
Yeah.
How do you know to pour in 50 ml of?
It's a 50 mil burette. So 50 mils is a good estimate of, right? It's the burette holds 50 ml.
So we pour in how much the burette holds?
Yeah. Yeah, you might as well. I mean, there's no point pouring in 100 because it'll just sort of spill everywhere. So yeah, I just poured in the volume it holds. It actually holds a little bit more, but you wouldn't want the volume to be up here, right? You wouldn't. So at the top, let me sort of zoom. Oh, damn it. Let me zoom in here again. At the top, notice that it sort of runs out of gradations when it gets to 0, right? So if we added more water, if we added more solution so that it filled it up to here, that's kind of useless to me because I can't measure this volume at all. I have no idea what that would be. So what I would do is I would just open up the stopcock at the bottom until the meniscus came down to 0, and then I would stop it and go from there. And then my volume initial would be 0.00. But what I'm saying is it doesn't need to be at 0. It can be anywhere because all you're going to be measuring is the difference between the final volume and the initial volume. That's the volume added. So this volume initial, it doesn't matter what it is, just as long as you measure it. That's all that matters. So you could add 49, you could add 51, you could add any volume you want. Make sure you add enough. That's just it. You just need to make sure there's enough for the titration.
So my other question is, if you put in 50 ml to a 50 ml burette, how did you end up with 2 ml initial?
Oh, because, here, let me show you. At the bottom of the burette down here, there's some dead space. Notice that?
Mm-hmm.
Let me clear it. Right there. See, there's some dead space right there. So that's just basically a little, you want to have a little bit of dead space there because you don't want it going to 50 and then stop and then, you completely run out of liquid. You want to give yourself a little leeway so that when you get down to 50, you say, oh, I need to add more solution. Yeah, you basically don't want it to right at the bottom because that'll change the shape of the meniscus. If it runs all the way out, your meniscus becomes flat rather than curved, and then you won't be able to measure it accurately. So that, yeah, there's a little dead space there. That's the only reason.
Wouldn't your initial reading be 50 ml if you poured in 50 ml?
No, it'd be 0. If you put, no, we put in 50 and our initial reading was 2.00. That tells us there's exactly 2.00 mils of dead space, right? Because we filled it with 50 and it left us with 2 mils left over. So this volume between the 50 and the stopcock is 2 mils. So you can
Okay,
add another
okay.
2 mils if you want to get to 0. It doesn't really matter. My point is, it doesn't matter what your initial volume is, because the total amount you're going to add to your solution is whatever the final volume you read minus the initial volume.
Okay.
Yeah, so this isn't important. It's important that you measure it. It's important that you measure it, but it doesn't really matter what it is. Okay? So let's do the actual experiment. All right, let's zoom out. So now I want to move. I got my burette. I got my, so I've been just do a check and everything. So I have my burette. It's got my hydroxide solution in it. I've got my beaker. It's got, I make sure it's got my acid in it. I'm going to click on it, make sure it's got my acid in it. Yep, low pH. And I'm pretty sure we added the phenolphthalein. Pretty sure we did. All right, so I'm going to drag my burette over the beaker. Actually, I should move the beaker up a little bit. So I moved the burette over the beaker. There we go. So before I add anything, I want to figure out how many moles of acid I have. That will tell me how many, approximately, what volume of base I want to add. What's the volume of hydroxide I want to add? How am I going to figure out how much, how many moles of acid I have?
Use the molarity concentration, the molarity formula, because you
I
have
only know the molarity of, I only know the concentration of the sodium hydroxide. I don't know what the concentration of, I don't know what the concentration of acid is in my beaker. I don't know what it is.
So you have to find the molar of sodium hydroxide first.
No, I don't know what the concentration. I know it's approximately 1 molar, but I don't know exactly what it is. The whole point is that I want to know what the concentration of the sodium hydroxide is. So I need to know how many moles of acid I have. That's known. My moles of acid is known. My moles of hydroxide is unknown. It's approximate, but it's not exactly known. How am I going to figure out? So I just told you this is known. How is it known? How do I know how many moles of acid are in there? What is my acid anyway?
KHP.
Right. So I added that. How much of that did I add?
You added 1 gram of it.
1 gram, 1.00 grams.
1.00 grams.
Here we go. Yeah, so I added 1.00 grams of KHP. How many moles is that? How am I going to figure out how many moles there is?
0.001.
Where
You're
did
gonna
that come?
take
Where did that come from?
204.22. No, one mole over 204.22
2422 what?
grams of KHP.
Right. I used the molar mass of KHP, so I want 1 mole, or what did you say, 204 point something?
204.22.
22 grams. So my grams cancel, and I'm left with moles of KHP. And how many moles is that? 1 divided by 204.22. So that's 0.0. Oh, go ahead.
0.00487 moles of
97
KHP.
moles. Yep. So at the equivalence point, that's my moles of hydroxide and my moles of KHP will be the same. So if this is the number of moles of my KHP, at the equivalence point, that will also be my moles of hydroxide. Now, if my concentration of hydroxide is approximately 1 molar, what's my volume of hydroxide that I need to get this many moles? Now remember, this is 1 mole per liter. So how many liters will I need to give me 0.004897 moles?
We will multiply.
Sorry,
What do
can
we
you
do?
repeat your question again?
Okay, I have a 1 molar solution of sodium hydroxide. That means I have about 1 mole per liter. I want 0.04897 moles of hydroxide, because that's the number of moles of acid I have. What's the volume of hydroxide I'm going to need to add? What's the volume of sodium hydroxide I need to add to get me 0.04897 moles? How many liters is that?
Would it be the same amount if you're trying to make it into 1?
It's 1 to 1, so it's the same amount in what?
Liters.
In liters, right. So it's 0.004897 liters. But this isn't liters, right? This is in milliliters. How many milliliters is that?
1,000 milliliters. 1 over 1,000, you have to multiply. No, you have to multiply.
Multiply it by, yeah, because I want mils, and there's 1,000 mils in 1 liter. So I would multiply this number by 1,000. So how many milliliters is that? So I move the decimal 3 places, right? I go 1, 2, 3. Put it right there. So 4.987 milliliters. So that's how many milliliters approximately I want. Because remember, I don't know exactly what the concentration is. I know it's around 1 mole per liter. I don't know, but I don't know it precisely. So what I want to do is get close to 4.9, but don't go right there. Go about maybe 85, 90% of the way. Don't go all the way, because you may have made a mistake in calculation. So what I'll do is I'll add like 4 mils right away and see if it changes color. And then if it doesn't, I will slowly add some more until it turns pink. Okay? So let's do that. So I'm going to add this 4 mils. 4.00 mils. Pour. Now notice that my volume dropped from 2 to 6. Do you see that on the burette? Everyone notice that? Yes.
The
no?
pH level
Yeah.
went up as well.
And the pH went up. That's right. So the volume dropped in my burette, which it should, because that's how much volume I added. The pH went up, because that's what we would expect happened. Anyone notice what happened to the temperature?
Temperature, it went up a little bit.
Went up a little, didn't it? Okay. So now there's two ways we can go from here. One, we can precisely add small volumes, or we can go to realistic and just press this. I find that a little dangerous because it's really tricky to get it to. I mean, if you ever like a really good pad or mouse or whatever it is you're using, you can add like individual drops. Mine, it either adds like a whole mil or it doesn't add anything. So I find it very confusing. You can play around with it when you do the experiment again later. But yeah, I find it a pain. So what I'm going to do is go to precise. I'm going to add 0.100. Actually, less than, let's go 1.050. And it's going to keep adding it and until it turns pink, okay? Okay. Notice, look at the pH. What's happening to the pH every time?
Go up.
It's going up, right? But has it turned pink yet?
No.
Actually, we could probably zoom in to see. Watch it turn pink. See if I can get everything in here. Okay, here we go. All right, I'm gonna keep adding. No, still not. Nope. Nope. Getting close though. Notice the pH is getting really close to 7. 6.38. 4.2. 4.7. So notice I'm getting really, it's slowly, no, because when you get to the, because where did we start? We started at pH like 3, like right around 3.3, something like 3.4.
Mhm.
And now we're getting really close to the point where the pH is going to change dramatically. And you can see that even adding very small volumes, I'm only adding like 1/2 of a 1/10 of a mil. Like these are really, really small amounts, and the pH is changing. And so when we get to the point, when we get to the inflection point, we get to the titration point, it's going to change big time. It's going to go from hit 7 and then go way above it. So it's super
I
close.
noticed that my pH level is not the same as yours. Is it different for everybody as well?
It would depend on the volume of water you used. If you use more water, the pH will change less. If you use less water, the pH will change more.
I use the same amount as you.
Oh, okay. How different is it?
So,
Wait, I may have just added more or less than you have at this point.
okay.
Right, 6.5, 6.6. Man, we're getting close. 6.7.
Mine turned pink when the pH level is 14.03.
Oh, it went way over. How much hydroxide did you add?
Same as you.
I don't think so. Oh, what are you clicking on? Are you holding it on the, because that's the pH of the, oh, damn it. I have to go back. That's the pH of 14 is the pH of the hydroxide. Don't put my burette back over it.
I'm at
There we go.
705 pH and I'm still not turning pink as well.
Oh, mine is 11.07 for the beaker when it turned
Yeah.
pink.
Yeah, it'll be a big difference. Was it just one click that went from clear to pink? Or was it a
No,
couple?
we're
It should be just one click.
around like 5 clicks.
Yeah, you want it to be clear, and then one click turns it pink. You've overshot it, but that's fine. You can do this as many times as you need to. Basically, what you want it to get down to a single click between clear and pink. That's why I'm using these really small volumes. So I'm going to go back to 0.05. So I'm going to keep going. Here's my beaker. Oops.
With me, mine turned pink like 3 clicks before it started to turn pink.
Huh? It started to turn pink before it turned pink? I don't understand.
No, sorry, I meant like it turned pink once it hit like the pH of 10.7.
Yeah, okay. Yeah, well, I'm going to see what I get. Right now, I've, 5. Okay, I'm going to pour it in there. So I'm at 6.8. I'm kind of curious to see what, so now it's still clear. 6.95. 7.09, still clear. 7.28. Now, notice how now that I've passed 7, each click changes the pH much more than it did before. Before, one click maybe changed it like by 0.1 or less than 0.1. Now every click's changing it by like 0.2 or more. Because now every time I add more base, there's no acid left. And now I've got more base. Now I'm just increasing the base concentration dramatically. So now so I think I'm probably right at I would say I'm probably at the equivalence point. I'm just going to add one more and see if it turns color. Nope, not quite yet. There it goes. Yeah, so in one click, in one addition, one small addition, it went from 7.8 to 10. So that's when the phenolphthalein changes color, when it's basic, when it's very basic. And it only takes a tiny amount, because at that pH, the concentration of hydroxide ion is really small. It's really, really small. I mean, look at the concentration of the sodium hydroxide, the pH of the sodium hydroxide. That's 1 molar. And that pH is 14. So the difference in pH here is 4. That's 4 orders of magnitude. Anyone know what an order of magnitude is?
Is it the difference between the pHs?
What's an order of magnitude? What's the difference? What's 1 order of magnitude? What's that a multiplication of? It's 10. So each pH unit is a difference 10 times of acid or base. So the concentration of base in my beaker is 10,000 times less than it is in the sodium hydroxide. So even a tiny changes the pH, dramatically. Okay. So, or the other way to look at it, just a small change in the pH represents a big change in the concentration. So, how much have I added? So, I would say I'm done at this point. My 1 drop went from clear to pink, so I'd say I probably did a fairly good job. So now I need to look at my burette and see what my volume is. What was my volume? All right, so here is my final volume. So remember, we started at 2.00, right? And what would you say the volume is now?
7.00 ml.
Yeah, I'd say that too. It looks like it's right on it. So my volume initial was 2. My volume final was 7.00. And so the volume of hydroxide I added was 5.00 ml. And if you remember, what did we calculate how much we would need? Do you remember?
The concentration of the base NaOH.
Do you remember what the volume of hydroxide we calculated at the beginning we would need to do the titration?
4.897.
Yeah, so we've calculated we would need 4.987 mils, and we wound up using 5. I'd say that's pretty close, right? So how are we going to figure out what the concentration of our sodium hydroxide is? How many moles of sodium hydroxide did we use in this reaction? So how many moles of sodium hydroxide did we wind up using for our reaction here? How did we calculate it?
0.004897 moles of sodium hydroxide.
And where did that come from?
The number we calculated, which is 1 gram of KHP.
Right, it's the same number of moles that are in 1 gram of KHP. Because remember, from our balanced equation, 1 mole of KHP plus 1 mole of sodium hydroxide gives us 1 mole of water and 1 mole of potassium phthalate. So it's 1-to-1 ratio. So give me the moles again. What was it?
0.004897.
4897 moles over, and my volume, remember, was 7 ml minus 2 ml. So that gives me 5.00 ml. And how many liters is this? Because remember, I want moles over liters. I need to convert my ml to liters.
1,000.
So 5 mils is 1,000 liters?
I mean, 0.005.
Right, so I multiply that by 1 over 1,000. Right, that gives me 1 liter, 1,000 mils. So that's 0.00500 liters. That is my concentration of hydroxide. So what is it?
So you divide the two numbers to get it, the molarity.
So what's my molarity?
For 0.9794.
0.9794. So M, capital M. How many significant digits can I use?
3.
Yeah, 3. Because basically I'm stuck with 3 significant digits to my volume. So what's my final answer?
But you know what, Professor? We add like 50 ml of something, which means 2 significant digits.
No, but yeah, we actually it doesn't matter. We could have just poured an unknown volume of NaOH solution into the burette because we measured the initial volume precisely, and we measured the final volume precisely. And it's the difference between those two that gives us the volume, not how much we poured in. We can pour in any amount. We could even like close our eyes and pour some in, as long as we can measure the initial and final volumes. So the 50 ml makes no difference.
So I have a question.
We always read the volume on the burette.
Okay.
So
If I'm getting-
oh, go ahead.
If I'm getting a different final volume reading as yours have, for titration 1,
Mm-hmm.
is it normal that I'm getting a different? I'm using the same exact numbers as you as far as
Okay.
putting the KHP.
Yeah, but yours titration is going to be slightly different. I mean, I was adding 0.05. You could have added 0.025. You could have tried the realistic and just like, do whatever you like. I'd like you to do 3 trials, and you can use different amounts of KHP. You can use, instead of 1 gram, you can use 1.2 or 1.5 or 2 grams if you want. Just calculate how much NaOH you're going to need. Like I said, go about 80, 85 of the way there, and then slowly add. I mean, you may be able to get a result more precise than this, because I was adding at 0.05 mils at a time. You might want to do it more slowly than that. You might want to go 0.025 mils at a time. You'll get a more precise answer. But what's my answer? What's the answer we came up with together? What's my final answer for the concentration?
0.979.
0.980 molar.
So it's 0.979 molar.
Oh,
This
79,
number is
sorry.
4. Yeah, so I would round it to 0.79, which you can see is pretty darn close to 1, but it's less, right? So what I would suggest is maybe, do a more precise job than I have here, and maybe you'll get closer, right? Because if I could have gone over by 0.05 because I was adding 0.05 at a time. If you add 0.02 at a time, you're probably going to get a closer answer than this. But that's not a bad answer, 0.979. I mean, that's pretty close to 1.
So do you want the answer to be 1.0?
No, it's not going to be 1.0. It's going to be less. Has to be. Remember?
So
Because we
you want
said
to be
when you make a solution base using water, that water is going to have acid in it. There's pretty much no way to avoid it. Just regular water out of your tap is going to be like pH 5 or pH 6. And in the lab, we use deionized water. I think I explained at the beginning. Deionized water is just basically a big contraption that takes all the metal ions out, but then it replaces them with H+. So deionized water has an even lower pH. And so if you use water that already has acid in it, and then you dissolve hydroxide in it, that acid's going to use up some of the hydroxide and drop your concentration. So that's why you need to figure out what it actually is.
okay. So you prefer to have less concentration than 0.9, correct?
No, it should be less than 1.
Okay.
Yeah, if you get a concentration greater than 1, you've probably done something wrong. Your answer should be somewhere between like 1 and like 0.95, probably somewhere in there. So do it 3 times, and your answer should be not that much different. I think if they're off by more than 5%, just do another one and drop the weird one, and then just report the average.
What about the weights of the beaker if we didn't take it in the beginning?
Weight of the beaker is not important.
So, because there's on your lab, we had to get the weight of the beaker, weight of KHP and beaker, and the weight of KHP.
Oh, yeah. That's a good point. I don't know if that's more accurate or not. I don't know if that's essential. You can try that. I mean, I just clicked on KHP and said add 1.00 grams, and it did that. So
I did that as well. So would I leave that part blank or?
You could try it the other way and see if you get a different result. Yeah, I forgot I put that in. That's because that's the way we would do it in the lab. So I just had the extra step. That's how we would do it in the lab. I'm not sure how important it is. You can try it either way.
How would we weigh the beaker? You just take the tool and then scale?
Oh, I don't think you need to weigh the beaker.
It is necessarily for our calculation or no?
Is what necessary?
The weight, to measure the weight
Of what?
of the baker and
No, I would think just taking, let's see, get rid of this, remove. So I think you put the scale on here and then go back to the solutions. Oh, glassware, other, weigh boat, you put that on there. And then you hit tare. So you get 2. You get that basically what tare means is that it subtracts the mass of the boat. And then you put the KHP on there. And 1.00, let's say 1.000. Yeah, it just gives you the mass. And I think you would just take this then, take the weigh boat and put it in your beaker. And then to take the weigh boat, put it over the beaker and just say, yeah, see, then it's just the same thing. Put 1.000 in there. So I don't think it makes any difference, basically is what I'm saying. I just sort of included those steps because that's what we'd actually do in the lab. So we just did a shortcut here.
so we could start our data just to start from the initial NaOH. If you check the worksheet, could you please check our worksheet
What worksheet?
in the paper of lab?
What about it?
So on part 1, standards is the data.
Mm-hmm.
Just want to see my paper.
I
Yeah,
think he's basically asking when we put our results like into the lab report,
yeah, this
we would only need to put in the stuff that we measured, like the initial reading, the final reading.
so
We
we
wouldn't
can just
necessarily have to worry about the weight, right?
Right. Yeah. Just yeah. If you don't use the beaker, just give me the weight of KHP. Actually, that should be grams. That should be mass, not weight. I think what it is that I took that from another lab that we actually, like a lab we did in IRL where we actually had the beaker and the KHP and everything else. So yeah, that won't be necessary. Yeah, thanks for pointing that out. I can take that out.
We're going to put the initial reading of the burette 2, and then final 7, and then MLNA.
Well, you're going to use your data, not mine. Use yours.
But it's like that, right? It's
That's
like
where
that.
it would go. Yes. Initial would be like, yeah. The initial should be lower than the second because the burette is labeled 0 at the top and 50 at the bottom. So the numbers get bigger as you go. So the initial reading should always be less.
Okay, thank you.
So we will start our data from initial NaOH. We don't need to fill the 3 part over.
I'm sorry?
In the
What-
table that you see now,
Yeah.
so I don't need to fill the first and second and third one. I will just start.
Third one you'd need, yes, you need the mass of KHP.
Okay, just the mass.
So the mass of KHP, you use the weight boat, right?
No, if you do, I mean, just put in a gram or whatever it is, a gram, 1.2 grams. Yeah, just basically give me like, the number of grams and how many significant figures you measured it to. That's another thing. You could measure it to 4 significant figures if you want. I think that's possible with the scale.
Okay, when you say the first titration and the second titration, so I will start to change the amount of everything from the beginning, or just when?
You can change the amount of KHP, or you can keep it the same.
Mhm.
Yeah, but each time, I don't know, try and do something a little different. Like try adding smaller amounts of the sodium hydroxide to see if you can get it even closer. Or maybe you could try just hitting the pour button and see if you can get it that way. Although, like I said, every time I try it, it just goes right to pH 12 or something. I have trouble getting that to work, but you might have better luck with your mouse or whatever you're using.
So for the mass of KHP, it's just 1.00 gram.
If you use that, if that's what you use, you're free to use a different mass. You can use twice that much. You can use 50% more than that. I wouldn't use less, but use between like 1 and 2 grams. You should get the same answer for molarity of NaOH. You'll use a different volume, but you should get the same answer for concentration. All right, shall we try the second one? Man, we're running out of time. Let's try the second one. So you basically do that one 3 times. That'll give you an average. So let's go to second experiment. So I'm just going to click on that one. And new share. All right, so can everyone see determine the identity of an unknown solid weak acid? Can everyone see that one?
Yes.
So this time we are given, notice that this time we are given a known concentration of sodium hydroxide. This time our sodium hydroxide is exactly 1.00. So presumably that has been determined through titration with something like KHP, okay? So what we're gonna do is basically the same titration reaction, but this time our acid will be unknown and our hydroxide will be known. So we're going to take this unknown solid acid. We don't know what it is, but we're gonna be able to measure the mass of it, okay? So go back to the stock room. I'm going to get my glassware. I'm going to get a beaker. Oops, only need one. I'm just trying to remember how much I put in there. I think it was 2. Did I say 2 grams? I can't remember. I think it's around 2 grams. If you look in the instructions, was it around 2 grams or was it less?
2.5.
2.5. Okay. Yeah, because I did this the other night. I can't remember. It may be different because I think everyone's going to get a slightly different acid than this one. Right. So I'm going to go over there and say 2.5. 0 grams. Okay. Take that away. I'm going to put some water in there so I can dissolve it. Let's say 50. I don't need that anymore. Now the pH of my solution, notice it's kind of the same as it was with the KHP. KHP was a weak acid and so is this. So now my pH is going to be less than 7, but not like crazy, like 1 or 2 or anything. So it's going to be, so it's a weak acid we have in there. So I'm going to go back to the stock room. Now I want to get my burette out. Other, burette. Oops, again, only need one. Yeah, there we go. And I'm going to put my 1.00 molar solution of sodium hydroxide in. And let's do 51 mils this time. And then put it over my, oh, what have I forgotten?
The indicator.
That is right. I forgot that would have been bad. I just remembered. That would have been bad. So let's put some, Raj. So let's put some phenolphthalein in there. Put a mil in. All right.
So for sodium hydroxide, you put 51 milliliters or 50 milliliters?
Put whatever you want. I just decided I'd put 51 and see if it went to 1 mil rather than 2. Let's see. Pretty sure it probably did. All right, let's drag it over. Yep, it's right on 1 this time. So I think if you put in 52, it'll be right on 0. I was just curious. So yeah, so I would put down my V1 and I zoom in to see what it is. And it is, yeah, it's 1.00, I would say. And that's the advantage. You can zoom in like really, really close to see exactly what it is. The other thing you can do, if you're clever, is to look at the volume of the beaker, 51.000. Except even if I'm adding the volume may be different. If I'm just adding like a liquid to a liquid, but a reaction is occurring too. And so, and the reaction produces water. And so if I just took the beaker's volume before and after, that may not be accurate because I'm producing water. So I think I will just take the volume of my burette as the accurate volume I'm adding. So let's try to remember, how much should I add? Was there an estimate of how much to add? I think it was around 15 or something, 15 mils.
Yeah.
Okay. I'm going to add 10 and just make sure. So 10.00. Pour it in. Okay, that looks, look at the temperature. What happened to the temperature?
Decreased.
It decreased?
It increased from
It
25.
increased. Yeah, it went up. Now, this is sort of moving ahead a little bit. But in this particular reaction, are we forming bonds or are we breaking bonds?
Forming?
We're forming. Yeah, we're actually breaking some too. We're breaking some of we're breaking weak hydrogen bonds with weak acid. Those bonds are weak, and we're forming strong hydrogen-oxygen bonds in water. So this should tell you a little something about where does, you know that some reactions are hot, right? We call those exothermic reactions. When they occur, they release heat. And so does the release of heat come from breaking bonds or forming bonds?
Forming.
Forming. And that's something that's really weird for us to think about, right? Like when you burn wood. When you're burning wood, it's nice and warm, you put your hands on it, and you think that the immediate thing that makes sense is that the fire is breaking all those bonds, chemical bonds in the wood, and that's releasing heat. That's not where the heat comes from. The heat comes from the formation of bonds in the CO2 and the water, which is weird to think about. But this reaction sort of shows you that that's really what it is, okay? So I added 10 and my pH went to 7. That means I'm probably fairly close, actually. I'm probably not that far from it. So I'm going to add like 0.5 and see what happens. Okay, so it went up a little, but not a whole bunch. So little. I'm getting there. Okay. Now when it gets to around 8, I'm probably going to like drop way back on the amount of hydroxide I'm adding. The other thing you can do is also you can do this over again. Don't refresh the page. If you refresh the page, or if you do this if you do like, let's say you do your first titration now, and then you close your computer and then you come back and you do it again, you're going to get a different result, because every time you refresh this page, you're going to be given a different weak acid to use. So be careful. So I'm getting really, really close. I think I'm going to go back down to like 0.200. Okay. Okay. Back up to 0.5, 0.300.
What if you're slightly pink, but not like
That's what you
dark
want.
pink?
That's exactly what you want. You want it to be, if it's dark pink, you've gone too far. You want it to be barely, if you're doing it in the lab, basically what we would do is we would take our beaker or our flask, we put like a piece of white paper underneath of it. So and then we'd be swirling as we'd be adding sodium hydroxide, because what you'll see is that with every drop of sodium hydroxide turns a small bit of the solution pink, because in that small part of the solution, the pH is really high. And then when you mix it up, it goes back low again. So when it starts doing that, that means you're really, really close. And so the perfect titration is basically you can barely see the color at all, but you know it's there. That's perfect. That's what we're looking for. 7.6. So man, I am getting close here. It's not pink yet, so.
What if my
Yeah.
pH was like 9.45?
Is it pink?
It's not it's not shot up. It's slightly pink.
That's it. That's perfect.
Even
yeah,
though
that's
it's
like I said.
more than 8.
That's exactly what you want. You want it to be just barely pink. If it's bright pink, it's too far. So mine, I don't think, actually I should zoom in a little bit.
Mine, it's slightly pink, but the pH level is 10.03.
Yeah, that's good. That's good, because it's going to change big time. I mean, I'm at 8 right now, so I'm going to back off and go to like 0.1, because it's going to change dramatically in a second. Still not pink. Almost. Yeah, it'll go from 8 to like 10. Come on. Can't tell. Does that look slightly pink? It's hard to see against the. They should have a white background here rather than a gray one. It would make it much easier to see. Because remember, I'm going to have a different result than you. So my weak acid is going to be,
That looks slightly pink.
Look like now it's okay.
yeah, when that went to 9. So it went from 8 to 9. So yeah, what I would do is that I'm not sure, maybe you have better eyes than I do. So what I would do is I would measure this volume. So I take my initial volume was 1. My final volume, I would look, and that looks like
23.00.
22 or 21.7. So we take it, so remember, we read it from, it's getting higher from top to bottom. So we've passed 21, but we haven't got to 22 yet. So that would be 21.70. So 21.70. So my total volume is 20.70. So what I will do is I will add one more drop. And if it turns bright pink, then I know that this previous result's the one I want. So what I'll do, that's now that looks pink to me. Yeah. So I think you were probably right. So it's either 21.70 or 21.80. I'll go with the 21.70 as my volume. Right. So what do I do with that information? So I have a volume of 20.70 ml and a concentration of 1.00 molar. So how many moles of hydroxide ion have I added to my reaction? So 1.00 moles per liter times what to give me moles?
It was the 0 point something, right? Let me look it up.
There's my volume. So what do I need to convert that to get me moles? Need to convert it to liters, right?
Yes.
So how many liters is that?
Ze- 0.0207 liters.
2, 3. Yep. So that gives me, and since it's 1 molar, that's the number of moles too. That's the nice thing about having a 1.00 molar solution. If you figure out the volume, that's also the moles.
So,
So-
did you get the 1 molar from the
That's the concentration.
1.00 NaOH?
That's the concentration of the NaOH. It's
Okay.
precisely 1.00 molar. So I have 0.002070 moles. What was the mass of my acid?
2.5 gram.
2.5 grams, 2.50 grams. Now, what is the number of moles of my acid? That's moles of OH. How many moles of acid do I have? So I know I measured 2.5 grams, but how many moles of acid did I measure?
Divide mass by volume.
What mass and what volume?
2.5. Is that the one you asked?
That gives me grams per liter. That doesn't tell me anything about moles. I need to know how many moles of acid I have. So I put a certain number of moles of acid in this reaction. How many moles did I put in there? How am I going to determine that? How did we determine that? What was the point of this experiment?
Is it to figure out the unknown?
No, yes, that's the overall point, but what was the point of putting the indicator and adding the sodium hydroxide?
The molarity?
What is that? Yeah, but we already knew what the molarity of the hydroxide was. What were we trying to determine? You're trying to determine something. What was it?
If the acid solution turns pink.
Yeah, what does that tell? Yeah, I mean, it turned pink. It would have turned pink anyway. If we just added, if we didn't add any acid at all, it would have turned pink. But what does that mean when it turns pink? That's the key thing. It turned
you
pink
have an
for a reason.
equivalent amount of NaOH and equivalent amount of unknown acid to get
That's
an even
amount. Yes, exactly. Amount in what? In what measure?
grams.
Reactions don't happen with grams. What do reactions happen with?
Mole.
Moles. So if we have this many moles of hydroxide that we added to that solution, how many moles of acid must have been there in the first place? This is how many moles of acid it took to neutralize that solution. How many moles of acid must have been there?
1.
Nope, because that would have taken us 1 mole of sodium hydroxide to neutralize it. It is a 1-to-1 ratio. That you are correct about. There's a 1-to-1 ratio between moles of acid and moles of hydroxide. So if we added this much hydroxide, if we added 0.002070 moles of hydroxide, how much acid must have been there?
Same?
The same. That's right. It's the same. It must have been this. It must have been this precise number of moles that we added to the reaction. Now, we didn't know that at the time, but we figured that out from doing the titration. That was the whole point of doing the titration, was to figure out how many moles of acid must have been there. So we figured out how many moles of acid must have been there. But we didn't measure moles of acid when we measured acid. What did we measure?
Moles of NaOH.
Oh, no, I'm sorry. What do we measure about the acid? What do we actually measure about it at the beginning?
The grams of how much we put in.
Right, exactly. So we measured grams, and now we've calculated moles. So now that we have grams and moles together, what can we determine?
We can determine the mole of the acid.
Yay! Yes, we can determine the molar mass. And now we have all the information we need to do that, because we know how many moles we have, because we figured out the number of moles, and we measured the number of grams. And molar mass is measured in what?
Moles. Grams over moles.
Grams over moles. There you go. So we have 2.50 grams of acid, and we know that we measured 0.002070 moles. So the molar mass is in grams per mole. And how much is that? Let's see. It's going to be a big boy. 2.5 divided by 0.00207. Dang, that seems big. Let's hope. I think I may have made a mistake. That comes out to 1,207 grams per mole. That seems high. Oh, this is probably 0.020. Let me make sure. Yeah, so I had 20.70 mils of 1 molar. I just want to make sure I got this to liters properly. 20.7. Yeah, it's 0.02. Duh. 0.0207 moles. Yeah, I was off by a factor of 10. See, that's what happens when you're in a hurry. So instead of 0.00, That makes a lot more sense. It's 0. It's 0.02 moles.
What? We
Because I
calculate
made a mistake converting my milliliters to liters. Because I had 20.70 milliliters of acid. And when you divide that by, when you multiply that by 1 over 1,000, you get 0.0270. I had 0.00270. So I was off by a factor of 10. So stuff happens. So it's not 120, it's not 1,207 grams per mil. It's 120.7 grams per mil. That makes a lot more sense. Per mole, sorry. 120.7 grams per mole. So what I can do is come down and actually ask it, is that right? I'm going to do that. So I'm going to clear and say, please enter your answer in the form below. The unknown solid acid is a molar mass of, I'm going to see if we're right, 120.7. Check. Oh, enter. Oh, he wants the pKa. I have no idea. Damn it. We didn't measure the pKa. Well, that sucks. So, yeah, so I guess you have to put the pKa in as well. That's something we didn't talk about. But that seems reasonable. 120.7 grams per mole. It's going to be somewhere between 100 and 300, probably. Your answer. And then remember, everyone's going to be slightly different. So do 3 titrations, and you should get pretty close to the same answer every time. What did everyone else? What did other people get?
Got 121 grams per mole.
Oh, so you probably had the same one I did then.
Yeah.
I had 104.60.
Okay. Oh, remember, yeah, we only have 3 significant digits. 1.00 molar. So I should have 121 too. You're up. See, you answered it better than I did.
But I had 104.
Okay. Yeah, it just means you had a different one.
Oh, okay.
Yeah.
How can I know my answer is almost close to the right thing?
We won't, unfortunately. We'll just have to go because we didn't calculate the pKa. The pKa is just basically remember the Ka was the value of how much the acid dissociated. And so if it dissociated a lot, it'd be close to 1. If it dissociated very little, it would be like 10 to the minus something. So the pKa basically is just a measure of how strong or how weak the acid is. If the pKa is very high, then it's a very weak acid. But
so is the mole of the unknown 0.0270 for you then?
Yeah, the number of moles of the unknown will be equal to the moles of sodium hydroxide you use to titrate it, because it's a 1-to-1. We assume it's a 1-to-1 ratio.
And is the mass of the unknown the amount that you put in, the 2.5?
Yes. Yes, you can use a different amount of unknown. You could use 3 mils or 3 grams, or you can use less. You can use 2 grams. Yeah, just be careful when you add that first bit of sodium hydroxide. That's just it. If you add like 10 mils of sodium hydroxide and it's already bright pink, well, then that's too much. Then just go back, empty that, put in another bit of acid, and just add less sodium hydroxide next time. Because 10's too much, so add 8, and then work your way up to 10. That's the nice thing. If you were in the lab and you added way too much sodium hydroxide, you have to dump it out and start all over. It would take you like a long time. Here, it just takes you 30 seconds to clear the workbench and just add new add new glassware. So it's much easier to do. But like I said, if you're going to do 3 trials, do them all at the same time, because if you refresh the page, you'll be assigned a new unknown. Okay. So don't worry. It's like, yeah, whoever said they got 104, that's probably right. Because they're all going to be slightly different. I think they're all going to probably somewhere between like 75 and 150, something like that. Because those are the typical sizes of the organic acids we use in labs.
So for the rest of the trials for both parts, we're just changing the grams of KHP and the mass of the unknown acid.
Yes, you can do that, or you can just repeat them by changing the value you use every time for addition. Like, so I was adding 0.1. You may want to use like 0.05 or 0.03 or whatever. See how close you can get. I think 121. That's pretty close. That's the right answer. Yeah, I'm sorry. I didn't realize we had to calculate the pKa as well. I thought we could just check on the molar mass. That's a drag, but I think any answer like between 75 and 150 is probably going to be pretty close. And the other thing, each of your 3 trials should give you the same answer. If one trial is dramatically different, just toss that one out and do it over. Just like here, you notice I made a mistake when I calculated my molar mass. I was off by 10 times. So when I did my experiment the next time, I would realize that, oh, if I have 2 answers that are 121 and the other one is 1201, yeah, it's pretty obvious which one is wrong. That's the advantage of doing everything in triplicate. Most scientists do all their experiments in triplicate, because if you do it twice and you get 2 different answers, you don't know which one is wrong. But if you do it 3 times and 2 answers are the same and the other one's different, well, then you know that's the one to get rid of and repeat. Okay? So does everyone have a fairly good idea what they're doing here? Yes, no?
Yes.
Yeah.
Okay, good. Oh, and I'll have an announcement coming up. Yeah, it looks like unfortunately, we're not going to be able to, it looks like our lab kits are probably not going to arrive in time. So that's a drag. So it looks like we won't be able to do the home experiments. So
it's gonna be online, yeah?
Yeah. So, I mean, we'll see. I mean, it's possible they might arrive next week, but if they don't, I mean, we're almost out of time. So we'll see. It's not looking good, though. I hate to say. Anyway, that's the way it goes. I think what happened is that there was so much demand on these companies. They basically promised everybody that they were going to ship them, and they just had way more demand than supply. And so that's probably what happened.
Honestly,
Anyway.
I like online because I just click on the amount. Like, I don't need to put
It's pretty easy to do, right?
Yeah.
You don't get your fingers all stained with like phenolphthalein stains your fingers, stains them all pink, and there's like and acid smells all kinds of nasty, and sodium hydroxide can burn you, and yeah, this is much better.
The only thing that we do not have like direct contact with you, like we cannot ask you question directly to show you.
Yeah, I mean, you still can, but yeah, it's more fun when you're in person.